The rank of a matrix. Row space, column space, and rank. We've already become familiar with what a basis is, and that is a set of vectors that will span a certain vector space. What we now want to look at is we want to look at a vector space spanned by rows or columns of a matrix. So for instance, just to be sure that we understand row and column matrices, we've got a row matrix of 1, 2, 3 and a row matrix of 4, 5, 6. They can be written just like that, or of course 1, 2, 3 as a row matrix as well. And then we have column vectors, which are just the columns of our matrix. Now what we want to do is we want to find the row space of A and the column space of A. And the row space of A is a subspace of Rn, where A is an m by n matrix. So rows, columns. The row space of A is a subspace of Rn spanned by the row vectors of A. And the column space of A is the subspace of Rm spanned by the column vectors of A. Now this doesn't make sense probably just in words, so let's take a look at an example. Before we look at that example, let's talk about three theorems that will come into play when we do that example. The first says that if an m by n matrix A is row equivalent to an m by n matrix B, so again we're saying we've got some matrix A, we do some row operations probably into row echelon form, then the row space of A is equal to the row space of B. So we're saying those two matrices, if they are row equivalent, will have the same row space. In addition, our second theorem says if matrix A is row equivalent to matrix B in row echelon form, then the non-zero row vectors of B form a basis for the row space of A. So what that's saying is when we get to B, we're going to look at any of those vectors, row vectors that are non-zero. So usually we end up with like 0, 0, 0, 0 at the bottom. So we're looking at the ones that are non-zeros. Those are going to be the basis for the row space of A. And finally, when we're talking about the dimension, we've already talked about the dimension and said that's how many vectors are in a certain vector space. So the dimension of the row space and the dimension of the column space are equal, and that value is known as the rank of a matrix. Now that we have the proper background, let's take a look at the math. So we're trying to find the basis for the row space of A and the column spaces of A, and then give the rank. So we're going to do the math first, and then before we go on to the next slide, we're going to make sure we understand the difference between row A, column A, and the basis for row A and column A. So let's start by just doing the math, which is to do the row reduction. So if A is this matrix, I'm going to start by taking the first row plus the second row. So I'm going to rewrite this first row. And then row 1 plus row 2 gives me 0, negative 2, 5, negative 6. And negative 5 row 1 plus row 3 gives me 0, positive 14, negative 35, 42. And then I'm going to continue. I could take a seventh times that last row, but I'm going to go ahead and just try to reduce. So I'm going to keep row 1 the same. 1, negative 4, 9, negative 7. Row 2, I'm going to keep the same this time. And row 3, I'm going to take 7 times row 2 plus row 3. So that's going to give me negative 14 plus 14, positive 35 plus 35, and negative 42 plus 42. And then I'm going to keep going just one more step, because remember, this is not REF yet, and I want it to be REF. So this is still negative 1, negative 4, 9, 7. I'm going to take negative 1/2, so that gives me positive 1, negative 5/2, positive 3, and this is 0, 0, 0, 0. So now I've done the math, and now I'm going to find the basis for row A. So the basis for row A is going to be using REF any non-zero rows. So the basis for row A is 1, -4, 9, 7, and 0, 1, -5/2, 3. Now, remember that the basis means that anything in row A is, you know, an unlimited number of solutions. Row A is every linear combination of these two row vectors. So any linear combination, I could take 2 of these plus 1 of these. I could take -2 of these, you know, -4 of these. We get the idea that the row space of A is all of those vectors. The basis is those linearly independent vectors that we can use to write all of the other vectors. The rank is the number of vectors in either the row space of A or the column space of A, which is 2. So there's 2 vectors here, and when we find the basis for the column space of A, there should also be 2. So now let's find the column space of A. Method 1, which is my preferred method, says do exactly what you would do to find the row space of A, and then determine which of these columns have the leading one. So the first column has a leading one. Some textbooks call that the pivot. And my second column has a leading one, and the others do not. And those are the 2 columns then that I am concerned about. But I'm not going to write them from row echelon form. I'm going to write them from the original matrix. So these are the first 2 columns in the original matrix. And so the basis for the column space of A is 1, -1, 5, and -4, 2, -6, the first 2 columns. Again, that's not column space of A, that's the basis for the column space of A. So column space of A would be any linear combination of these 2. So C1, V1 plus C2, V2 is the column space of A, where C1 and C2 are any real numbers, and V1 and V2 are those 2 column vectors. There is also another way to find the column space of A using the transpose for A. I don't prefer this method because I'm already doing the work to find the row space of A, so I might as well just use that same work for the column space. But the other way is to take A and write the transpose. So 1, -4, 9, -7, -1, 2, -4, 1, 5, -6, 10, 7, again because the transpose is taking rows and turning them into columns and vice versa, and then doing the math again to row reduce. So if I row reduced this, I would have 1, -1, 5. I would add 4 of row 1 to row 2 to get 0, -2, 14. I would take -9 times row 1 and add it to row 3, so that's 0. +9 plus -4 is 5, and -45 plus 10 is -35. Then I would get 7 times row 1, so 0, -6, 42. And then I would continue to row reduce, 1, -1, 5. It looks like I can take the second row times -1/2 to get 0, 1, 7. Just in my head, I can see that this is 1 times 5. Oh, this is -7, sorry. That these are opposite signs, 5 and -35, -6, 42, and that if I take these times 7, I'm going to get the other one, so I'm going to get 0, 0, 0, 0, 0, 0. And so what's the point of all of that? Well, now I have, this would be the row space of the transpose of A, which is the same as the column space of A. So the basis for the column space of A would be using the transpose of these, which is 1, -1, 5, and 0, 1, -7. Now you might be saying, well, that's not the same 2 that you used before using method 1, and that is true, again, because we continued to row reduce. But what I can tell you is the 2 vectors that we had before, which was 1, -1, 5, and -4, 2, -6, I would be able to still write these two a linear combination to get either of these rows. Here's a question for you to try on your own, and really the point of this question is not for you to do the row operations, because I've given you that A is equivalent to B, and B I've already written in row echelon form for you. So what I want you to do is to just know, how do I find the basis for row A, how do I find the basis for column A, and how do I determine the rank? So once you've done those 3 things, press play to see how you did. So again, since we've done all of the work already, the row space of A is the non-zero rows in row echelon form. So the basis for the row space of A, again, that means these are the vectors, row vectors that would span all of A, and that is 1, 3, -5, 1, 5. That's that first row in row echelon form. The next non-zero row is 0, 1, -2, 2, -7. And the third non-zero row is 0, 0, 0, 1, -5. Now, I want you to note that there are 3 vectors. So the rank of A is 3, which means there's 3 vectors in the basis for the row space of A, and for the basis in the column space of A, there should also be 3 vectors. Now, how do I find the vectors in the column space of A? I look at the row echelon form, not reduced row, but row echelon form, and just find those columns, find the columns that correspond to the rows with a leading 1. So this one had a leading 1 here in the first column, this one had a leading 1 in the second column, and this one had a leading 1 in the fourth column. Those are the 3 column vectors that I want, but I have to translate them back to the original matrix. So I'm going to use the first column, but in the original matrix, so that's -2, 1, 3, 1. The second column, -5, 3, 11, 7. And the fourth column, 0, 1, 7, 5. Again, those columns correspond to those leading 1 columns, sometimes called pivots. Some of the textbooks call these leading 1s pivots. So we're looking for the columns that contain the pivot. Again, I want you to note there's 1, 2, 3 column vectors in the basis of column A, and that corresponds to the rank. The null space of a matrix. The null space of a matrix is the set of all solutions of the homogeneous system of linear equations AX = 0. So what we mean by that is we've already learned how to solve a homogeneous system. And we said the homogeneous system is when AX is equal to 0. So what we're looking for is any of the vectors in Rn which would map to 0. Now, it can get a little confusing when they're talking about m by n and so forth. So let me help you hopefully try to make sense of this. This is Rn and this is Rm. Rm is where the 0 matrix would be. Now, why do I know that? Think about, say, a 2 by 3 matrix. Let's say this is 2 by 3. So a 2 by 3 matrix would have 2 rows, and I'm just going to call it A11, A12, A13, A21, A22, A23, because I don't want to focus on the numbers here. I want to focus on how many rows and columns. Now, if we're setting up the equation, this is ax equals 0, what would be the dimension of x? Well, x would have to be a 3 by 1 matrix. How do I know that? Because in order to multiply matrices, if it's got 3 columns in the first matrix, I need 3 rows in the second matrix. So that's why they're saying the null space is a subspace of Rn. So Rn is going to be 3 by 1 matrices. And it's denoted by null A. So what we're saying is this is Rm. Rm is going to be where the solution set is. So if I multiplied these two, what would 0, 0 be? Would it be 0, 0, or would it be 0, 0, 0? Well, if I multiply these two, I'm going to get a 2 by 1 matrix. So in this case, notice that would be the 0 matrix, 0, 0. So hopefully that helps you understand the m's and the n's. But essentially what we're saying is we want all of the matrices, all of the vectors that make this equation true. Before we find the null space for A, I want to point out that A is row equivalent to B, which is row equivalent to C. And A is my original matrix, and B is in row echelon form, and C is in reduced row echelon form. And it's very important to understand this because you can use each of these matrices for different things. When we were finding the column space of A, we used columns from the original matrix. When we were finding the row space of A, we were using REF, row echelon form. When we find the null space of A, we're going to use reduced row echelon form. Now, the great news here is that you already know how to find the null space, you just don't know that that's what it's called. So we've done this before where we said, okay, let's go ahead now and write this solution parametrically. So think about having this augmented with 0, 0, 0 because that's the solution. Remember, for a null space, we're saying that AX is equal to 0. So to find the null space, we're taking each of those rows and writing them as equations. So this is x1 plus x3 plus x5 is equal to 0. So that's that whole first row. And then I'm going to do the same thing for the next row, again, from the RREF form. So this is x2 minus 2x3 plus x3, x5 is equal to 0. And then x4 minus 5x5 is equal to 0. And then I have zeros. So I want to write each of these values isolated. So for x1, to isolate x1, I would subtract x3. We're going to call x3 s and x5 t. So x1, instead of minus x3 minus x5, is minus s minus t. x2, I would add two x3s to each side, which would be 2 instead of x3. We're going to call it s. And I would subtract 3x5 or subtract 3t. And x4, I would add 5x5 or 5t. So this is going to be my solution, but of course I'm not going to write it like that. And I want to find the basis. So let's keep going. The next step would be to write this as S times some vector plus T times some vector. So for S, I've got -1, +2, +1, 0, 0. And for T, I have -1, -3, 0, 5, oops, I forgot my 0, 0, 5, 1. Now keep in mind that this was a 4 by 5 matrix, and so it makes sense that my solutions are 5 by 1 matrices. So when it says find the basis for the null space, the basis are the vectors that I've just created, writing this parametrically. So the basis would be -1, 2, 1, 0, 0. That looks like an 8, but that's 2 zeros. And -1, -3, 0, 5, 1. So what we're saying is that those two matrices span all of the solutions of AX equals 0. Let's do another practice together where we're doing the math. So we have A, and I want to find the basis of the null space of A, and then they're just giving us another term here. The nullity of A is just the number of vectors. So the same way we said the rank of A is going to be the number of vectors in the row space or column space. The nullity is the number of vectors in the null space of A. So let's go ahead and row reduce A. -3 times that first row plus the second row would give me 0. And then -6 plus 6 is 0. And then 6 plus -5 is 1. And then -3 plus 4 is 1. And then let's take negative row 1 plus row 3 to give me 0, 0, 2, 2. I can see that the last row is going to go away completely. It's going to 0 out. And so this guy is going to be 0, 0, 1, 1. I'm going to take -2 times that row to get 0, 0, 0, 0. And remember, this is REF, but I want to find reduced row echelon form. So I have to keep going using this one right here. So I'm going to take 2 times row 2 and add it to row 1. So this guy's going to remain the same, and then I would get 2 plus -2 is 0, and then 2 plus 1 is 3. This guy is still 0, 0, 1, 1, and this is 0, 0, 0, 0. So this is RREF. Now, when I'm finding the null space of A, I'm using RREF. So taking that first row, I have x1 plus 2x2 plus 3x4 is equal to 0, because remember, think about it augmented with zeros. For my second row, I have x3 plus x4 is equal to 0. So that means if I'm writing this as x1, x2, x3, x4, x1 is, we're going to let x2 be s and x4 be t. So x1 would be -2x2, so -2s, and then -3x4 by moving it to the opposite side of the equal sign, so -3t. And x3, I would simply subtract x4 from each side, so that would be -t. So my solution would be s times some vector plus t times some vector, and those two vectors are going to be the basis for the null space of A. So for S, I've got -2, I've got +1, I have 0, 0, and for T, I have -3, 0, -1, 1. So the basis for the null space of A are those two vectors, negative 2, 1, 0, 0. Man, with the 8s and the zeros. 0, 0. Negative 3, 0, negative 1, 1. And the nullity is 2 because I have 1, 2 vectors. Here's a check for understanding. What I would like you to do is determine, however you might know how, if U, which is negative 5, 3, negative 2, is in the null space of A, where A is the matrix that I have given you. So I'd like you to press pause, try this question on your own. When you're ready, press play to see how you did. Now, one way to do this, which is the long way, is the way that we have been doing this, which is to take the matrix A, row reduce it, and notice I didn't show the work there, but I row reduced it to this matrix, and then wrote the solution parametrically, which was to say that x is equal to some parameter s, or t, whichever letter you chose, and then 5 halves, negative 3 halves, 1. So this is what we have been doing, is writing our solution like this, which would make this matrix the null, the basis of the null space of A. The question is, can I take that basis and write matrix U as a linear combination of this matrix? And the answer is yes. If I let s equal negative 2, then I get negative 5, 3, negative 2. So it's great to do it that way because first, we know how to do that. It's row operations. Second, we know how to write it parametrically. And third, we're putting together that this matrix, this vector, can span any of the solutions in null A. So any solutions in null A, I should be able to write using some value of s, which would be a linear combination of that matrix. The second way to do it is, if you did it the second way, great work, because not everybody puts together that the null space of A is all of the matrices such that A times x is equal to 0. So in this case, we're saying, is U in x, or is A times U equal to 0? And if A times U is equal to 0, then it's in the null space of A. And so that's the short way, which is just multiply it out, and we find 0, 0, 0. So yes, either method that we choose, U is in the null space of A. So putting it all together, this is a great practice. If you feel comfortable, feel free to skip this question. But this one, you're going to do all the parts. You're going to do all the row reduction. You're going to find the basis for the column space, the row space, and the null space. You're going to find the rank. You're going to find the nullity. And you're going to verify that n is equal to the rank of A plus the nullity of A. Remember, this is m times n matrix. So press pause. Take a few minutes to do all of that work, and then when you're ready, press play to see how you did. So I'm going to go ahead and start the row operations up here because I know that we're going to run out of room. So I have 1, 0, negative 2, 1, 0. I'm going to keep row 2 exactly the same. I'm going to take 2 times row 1 plus row 3, so that gives me 0, negative 1, negative 4 plus 1 is negative 3, 2 plus negative 1 is 1, and 0 plus 3 is 3. And then I have 0. I'm going to go ahead and take this one times 1/3. So 1, 3, 0, negative 4. So I'm doing a lot of steps on each step, but that's because there's going to be a lot of row operations. Let's continue. I have row 1 where I want it for now. Row 2, I'm going to keep it that, I'm going to go ahead and take it times a negative 1. So that's going to be positive 1, positive 3, negative 1, negative 3. That looks like a 10, so let's make sure we're clear. I can see that these two are the same, so if I take a negative row 2 plus row 3, I'm going to get 0, 0, 0, 0, 0. And this one I'm going to remain the same for now. Continuing my work, my first row gets to just hang out until the end. My second row I'm going to keep as it is. I'm going to switch row 3 to row 4 because I want all of the zeros on the bottom. And then I've got 0, 1, 3, 0, negative 4. So from here, if I wanted to, I've tried not to do too much on any one step, but I could have taken negative row 2 plus row 4, which is what I'm going to do now. I'm going to keep row 1 the same. I'm going to keep row 2 the same. I'm going to take negative row 2 plus row 3, so that's going to give me 0, 0, 0, 1, negative 1, and then 0, 0, 0, 0, 0. Hopefully I can fit all of this in. This is row echelon form. And then reduced row echelon form would have a 0 here, which we already do, and zeros here. So that's what I'm going to do next. So I'm going to take row 3 plus row 1, so that's 1, 0, negative 2, negative row 3 plus row 1. So that's going to give me 0 and then 1. And then to get rid of this one, I'm just going to add the 2 rows together. So that's 0, 1, 3, 0, negative 4. And this is 0, 0, 0, 1, negative 1, 0, 0, 0, 0, 0. Woo! And that is RREF. So now let's see if we remember how to do all of the things. I'm going to start with the basis for the column space of A. No, I'm going to do row of A first because that's the easiest one. So the basis for the row space of A is going to be the non-zeros, non-zero rows, which is which is in REF. 1, 2, 3. So that gives me 1, 0, negative 2, 1, 0, 0, 1, 3, negative 1, negative 3. And I'm going to put the last one up here because I'm running out of room. 0, 0, 0, 1, negative 1. Okay, so I've got 1, 2, 3. That means the rank of A is 3. What's N? Remember there's 4 rows, 5 columns, so this is 5. So that means this should be 2. Which means we should have 2 when we find the null space of A, which we'll do in a little bit. Let's find the basis for the column space of A. The basis for the column space of A should be any of the columns that include the leading 1, which is 1, 2, and 4. So I'm going to use my original 1, 2, and 4. So the basis for the column space of A is 1, 0, negative 2, 0, 0, negative 1, negative 1, 3, and 1, 1, negative 1, 0. Again, there were 3 of them, which is what we expected because the row space and the column space should have the same number of vectors in their basis. And now we have to finish with the null space of A, the nullity, and of course the basis of the null space of A. So that would be using this final reduced row echelon form. I'm going to write this as x1 minus 2x3 plus x5 is equal to 0. x2 plus 3x3 minus 4x5 is equal to 0. x4 minus x5 is equal to 0. And that gives me, let x3 be s and x5 be t. So x1 is equal to positive 2x3 minus x5. x2 is equal to negative 3x3 plus 4x5. x3 is equal to s. x4 is equal to negative x5. Oh, sorry, positive x5. And x5 is equal to t. So the basis, well, let's go ahead and go to the next step. So x is equal to s, 2, negative 3, 1, 0, 0, and t, negative 1, positive 4, 0, 1, 1. And then that means the nullity is 1, 2, which is what we expected. And the basis for the null space is those two vectors that we just came up with. Positive 2, negative 3, 1, 0, 0, and negative 1, 4, 0, 1, 1. Woo-wee! I can't believe we got it all on one page. Hopefully that all made sense to you. So we have the basis for the row space, the basis for the column space, the basis for the null space, which is the group of vectors that we can multiply by any scalar multiples to come up with any vector that's in the row space, column space, or null space, respectively. Non-homogeneous systems of linear equations. We've done a lot of work lately on how to find the solution for a homogeneous system of equations where ax is equal to 0. Now we want to take a look at the non-homogeneous system where ax is equal to b. Now, the good news is the way that we've been solving for when ax is equal to 0 is similar to what we're going to do here. We're going to find that the solution for every solution to a system can be written as the homogeneous solution plus the particular solution based on the value that we are given in the constants. So what we're going to do is we're not going to do a lot of the math because this is a very long video because we're doing a lot of the math by hand in this video. But what we're going to do is we're going to say here's the system: 1x1, negative 2x3, 1x4 is equal to 5. And notice I've just translated each of those into a row in matrix A. And then I did the work to turn this into reduced row echelon form, which is what we did before when we were finding the null space or the basis of the null space and so forth. So I'm going to do this the same way that we did before, which is 1x1 minus 2x3, taking this first row, rewriting it as an equation, plus x4 is equal to 5. So now instead of equal to 0, it's equal to 5. And then I've got x2 plus x3 minus 3x4 is equal to negative 7. And then I've got x3 is free and x4 is free. So I'm going to rewrite this as 5 and then plus 2x3 or 2s minus x4, so minus t. x2 is equal to negative 7, and then I've got plus x3, so I'm going to subtract it, so minus x3, and then minus 3x4 means plus 3t, and then x3 is s, and x4 is t. Now when we were doing this before, the 5 and the negative 7 would have been zeros. So the way that I would have written this for ax is equal to 0, or the homogeneous system, would have been s, and then I would have 2, negative 1, 1, 0, and then t, and I would have negative 1, 3, 0, 1. This would have been my solution to the homogeneous system. This is considered x sub h. So all this is saying is, guess what? You can't forget that you have this 5, negative 7 here. So the particular solution is 5, negative 7, 0, 0, because there's no numbers here, plus the homogeneous system. So this is the particular solution plus the homogeneous system. I believe we've already answered questions in this way, but it's important to understand how these things connect. In another edition of These Things Mean the Same Thing, we have if A is an n by n square matrix, then the conditions below are equivalent. A is invertible. Ax equals b has a unique solution for any n by 1 column matrix B. Ax equals 0 has only the trivial solution. A will row reduce to the identity matrix of size n. A is not equal to the 0 matrix. The rank of A is equal to n. The n row vectors are linearly independent, and the n column vectors are linearly independent. Up next is section 4.7, coordinates and change of basis. And again, we are using Elementary Linear Algebra 8th edition by Ron Larson.